Alright, this one should be a quick one. I just wanted to show the difference between P-core and E-core on some recent-ish CPU of Intel's. So if you don't know, like the newest CPU of Intel, I think I forgot which generation it is. You should look your own CPU to know if it's part of this, but they have P-core, so performance core, which are the cores that can actually have higher clock speed, and they have hyper-threading. And they have E-cores, which are efficient core, but basically the efficient core are just like a lower clock speed and they don't have hyper-threading. And so they're much slower, and they're meant to be like running background tasks, while the P-core handle like the heavy-duty tasks. And so I have one of these CPUs, I think 12th generation i5 or something. And anyway, we can see here that if I do LSCPU like this, we can see that the first 12 cores are my P cores because the max megahertz are higher, and the last 4 are E cores because you can see that the megahertz are 3600 instead of the 4900. And so I just wanted to quickly, I don't know, on stream I was playing around with CPU affinity, which just means that you can specify on which CPU cores your program can run on Linux. And so I was wondering, what is the actual performance difference between E cores and P cores? And looking at the megahertz like this, it seems to me like it should be negligible, you know, and it should be like, what, a third, or like, I don't know, even, no, a quarter of a difference or something like that. So not too big, but it turns out that I was surprised by the result. And so I have a little program here. Let me just quickly go through it. I just get on which CPU I want to run this on. So CPU in this context just means the CPU core or CPU thread. So this column, this CPU column. And so you have a CPU set where you can say which core or thread you can run on. And so you initialize it to 0, you enable the CPU that you want to run on, and then you use this schedule set affinity for the current process. So 0 means the current process, and this just means like the current process can only run on this core. And then I have a very silly benchmark thing that just does a huge sum for this many times. And so anyway, I compile it like so, fully optimized and so on. And if I run it on a performance core, 0, first off, let me show htop, so to show that I'm not lying, it's gonna spin up only the core, the first core, like so. You can see that it takes about 3 seconds, but if I go on core 14, which is an efficient core, so again, it's showing up only on the efficient core, but you can see that it takes much longer. Like not 25% longer, like not what I would have expected with the megahertz. And you see that it's actually using the megahertz, like the maximum available speed, you know. But it took 13 seconds instead of 3 seconds, which is very surprising to me. So anyway, if you have like a performance critical application or something, and you have one of those types of P and E cores on your CPU, which of course, I don't know, on servers CPU, I'm pretty sure that they don't have it, but if you're just a regular guy and you have a regular CPU, there's a good chance that you have those, and so you may want to look into that. Maybe running only your application on P cores, or if it's a background thing, only running it on the E cores, and so on. If someone in the comments can explain to me why the difference is so huge, even though there is only like 1000 megahertz difference, that would be nice, because well, I should have done some research before this video, but I was too excited. So anyway, if someone can tell me why there is such a huge difference, that would be cool. Anyway, that's it. I just wanted to show that there is a big gap between P and E cores. I hope you liked the video, and I'll see you in the next one.